going to move on now to the next theorem. This theorem is the limit of a function involving a radical. Let's just kind of highlight some things here. Again, n is a positive integer. Once again, we're not going to use any values of n, like the root index being a fraction or whatever. The following limit is valid for all c if n is odd, but it's only valid if n is even for the value of c to be greater than 0. Now let's look at that. If n is odd, then the limit is valid for all values of c. If n is even, then it's only valid for those that have a positive. If you think about it, if we're taking the square root of x, then we would have to make sure that our radicand, the value inside, is a positive quantity, and so that's why the value c has to be positive. Here's an example then that we can look at. Let's consider the limit as x approaches -8, and let's look at this as the cube root of x. So if we're looking at this, it says that we have a limit. And how would you describe the process of finding the limit? Let me call your attention to the fact that the inputs are approaching this value c, and it appears, and it's true, that we are using direct substitution. Okay. So this would be then the cube root of -8. Is that a valid? Well, let's see. N, our root index is odd, so therefore it should be, and the question is what number multiplied to itself 3 times is -2, or excuse me, -8, and the answer is -2. If we look at another example, let's let the limit as x approaches -4. This time, let's look at the 6th root of x. 6 is even, so we have to make sure that our value is positive. This would give us the 6th root of -4, which is undefined in the reals. And we'll say in the set of real numbers. Okay, let's see what happens on the Inspire, just to make sure that we've got this. Let's go to our template, and let's see, the first one is x, and we are approaching -8. Just want to call your attention, remember you have to use the change of sign key. So -8, and then we're going to look at this for the cube root. So what we have to do is go to the icon that the control on the exponential that allows us to put any root index in. So we have then the cube root and then tab to get inside the radicand of x, and our answer is -2, as we expected. And we'll do this one more time. We're going to have x, and it's going to be approaching -4. And now we're going to have the 6th root of x, and our answer comes up to be non-real result. We could find an answer if we wanted to change the mode. We're going to stay in the real numbers, so we'll accept the fact that it is non-real. Okay, so this is a theorem that just allows us and makes it a little easy to think about radical functions. Let's move on. Now, at any point in this video that you need to have me slow down, you want to go back over something, you have the ability to do that. So this is one advantage over having me right there with you in class today, is that you can rewind, look at it again, and take it at your own pace. Okay, let's go on though. Theorem 2.5, the limit of a composite function. We know that a composite function is a function within a function. So let's do another matching here. if f and g are functions such that, and what we're going to say is such that the limit of g of x as x approaches c is L, and the limit of f of x as x approaches L. Now I'm going to move that so you can see. There we go. Hopefully see all of that. I'm going to take that away. Then we'll take that away also. Okay. Notice that here we are approaching, let me just kind of highlight this. Here we're approaching a value C, and the output is, we'll put this one in green, the output of the limit is L. Notice down here that our inputs are approaching L. So again, as a composite function, if we're working first with the function g, its output is going to be the value that becomes the input of the second function. So if we have this situation occurring where the function g of x has a limit as x goes to a destination of c, and that value is L, and we have another situation where the limit as x approaches the output of g of x, then here's our conclusion, and we will take that away also. Here's our conclusion. Then the limit of the composite function f of g of x is the same as first taking the limit of g of x using that result in function f. Now let's look at an example of that, and that's on the next page. So we're going to use this idea. Well, I'm going to put it here so we can keep that theorem in front of us. Let's let g of x is going to be x squared plus 4, and f of x is going to be the cube root of x. Okay, we're going to take the limit as x approaches 5 of g of x. Now if we look at that, g of x is just a polynomial, so that allows us to use direct substitution, and that'd be 25 plus 4, or 29. If we now want to do a composition, we're going to have to start with the limit as x approaches. Now we can't use 5. 5 is what we were using to approach g of x. Its result was an output of 29. If we're going to use the model we have up here, where we have f of g of x, we're going to have to take the output of g of x as the input of function f. So we're going to say the limit as x approaches 29, and this is going to be then the cube root of x. That's a radical. We just had a theorem that said that unless it's undefined, we can just use direct substitution. So we have then the cube root of 29. Now let's look at it in the other format here. So we'll just put a little line down here, and let's look at it using our theorem. It says that if we look at the limit as x approaches 5 of f of g of x. Now if we look at f of g of x, that's f of, and g of x is x squared plus 4. Now let's do our steps here. This would be the limit as x approaches 5. What is f of, let's go back and put this inside brackets. What is f of x squared plus 4? Well, This is my input, remember. X squared plus 4 is the input that I use in function f, so this would be the cube root of x squared plus 4. Again, if I can do this without having the even root index with a negative radicand, it's just fine, which in case it is. Now remember, look what I'm doing. I've got the direction I have. I'm still telling myself I'm working for a limit. Here it is, I'm working toward a limit. At this point, though, I am going to take the limit by using direct substitution. And the answer is going to be the cube root of 29. Okay, let's do one check over here. If we look at, and let me go back to the other Inspire here. If we do a template and we pick up a limit, we are looking at x approaching 5. And we are considering then the cube root of x squared plus 4. And our answer is the cube root. Remember, we have 29 to the 1/3 power, so that would be the cube root of 29. Okay, so that's how we're going to deal with the limit of a composite function. Now, the type of problems that you are going to be working on would be something like this. As x approaches 4, what is the cube root of x plus 23? Recognizing that we have that theorem that says if it's a radical and if it's an odd root index, the only thing we have to do is use direct substitution. So we would end up with the cube root of 27, and if we resolve that, the answer is going to be 3. We can also look at individually. We would have f of x is the cube root of x, and g of x is x plus 23, breaking that into two different functions, and f of g of x would be f of x plus 23, or the cube root of x plus 23. Okay. If we look then at taking the limit of g of x as x approaches 4, we would get r27. We would have then the limit as x approaches 27. Cube root of 27 would be equal to 3. Okay. We're going to stop this session for now, and we'll pick it up in the next session. So part 2 to come.